Okay, before we get back to circuit analysis, I want to do a couple examples of how you can actually use Laplace transforms to solve differential equations. Now, if you've been in a differential equations course, you know another way to solve these. These are just going to be second order, constant coefficient, homogeneous differential equations. So, quite frankly, what I'd call fairly simple to solve. So, let's look at an example here. So, we have f double prime at t plus 3f prime at t plus 2f at t equals 0. And we have the initial conditions that f at 0 minus is equal to 3 and that f prime at 0 minus is equal to 5. And then we're going to solve using Laplace transforms. Now, as I said, if you've been in a differential equations course, you already know how to solve this by writing down the characteristic equation, all sorts of things like that, finding the correct form, doing all of that good stuff. But we're going to do it using Laplace transforms. Now, it's definitely not going to look like it's quicker using Laplace transforms, but this is really just to get us used to using Laplace transforms so that we can use these for circuit analysis and for transfer functions. So it's not that, oh, this is a quicker method. It's really so that we get used to using Laplace transforms. So basically, if I want to use a Laplace transform, I take a Laplace transform of my differential equation, and then I just go ahead and use some of those properties, because I start with a second derivative. And remember, we have that table here where we know what happens if you get a second derivative. So I'm going to go ahead and kind of write these in brackets here just so that we can see everything. So what I'd have, I don't need my initial condition still, is I would have s squared capital F at s minus s f at 0 minus f prime at 0 minus. And now this is just for f double prime. And then plus 3. And then f prime would be s capital F at s minus f at 0 minus. And then the Laplace transform of f at t would just be f at s. Now, we didn't talk about this, but the Laplace transform of 0 is just going to be 0. If you plug the 0 into the integral, you're just going to be integrating 0, so you get 0. And now what I'm going to do is I'm going to plug some numbers in here and multiply a few things out. Well, let me just plug numbers in first. So if I plug my numbers in first, I'd have s squared f at s minus, okay, well, I have 3 here, so 3s, and then I'd have minus 5 plus 3 s times f at s minus 3 plus 2f at s equals 0. Okay, so then I'm going to solve for f at s, because f at s, is my solution, but it is in S domain. So that's the only issue with it, is that it is the solution to the differential equation. It's just not in the correct domain. So if I'm careful here solving this, I would wind up with s squared plus 3s plus 2 times capital F at s, and then I'll write one more time here, minus 3s minus 5, and being careful, 3 times 3, that'd be minus 9 equals 0. And then just solving this, f at s is equal to 3s plus 14 over s squared plus 3s plus 2. So this is my solution. This is my answer. But again, it's not in the right domain, so I have to put it back in the time domain. Now, I'm going to want to do an inverse Laplace transform with this. Now, if I go to my table here, I don't have anything that's in a nice quadratic form. In fact, what do I have? I have things like s plus a. I can't do the s squared because it's not, remember, these are all multiplied. You know, s plus a squared, or s squared plus omega squared. Oh, I've got an s plus a here. So, in other words, what I'm wanting to go back and get in the habit of doing is factoring. So f at s is going to be 3s plus 14 over, well, this would just factor to s plus 2 times s plus 1. Okay, but I'm still not ready to write a solution down because I need to break this apart so that I can use my Laplace table, and so this is actually where we're going to bring up partial fraction expansion again. And so I'm saying this is definitely not necessarily a shorter way of solving the problem, but it is using Laplace transforms to solve the problem. So then what we'd have here is f at s would be, for instance, a over s plus 2 plus b over s plus 1, which of course is equal to 3s plus 14 over s plus 2 times s plus 1. And then this is where, you know, doing the partial fraction expansion, you'd clear out the denominators and you'd have s plus 1 times a plus s plus 2 times b is equal to 3s plus 14. And this is where I choose smart numbers. So let's choose s equals -1, because then if I choose s equals -1, the a is just gone, and I'd have 1 times b is equal to -3 plus 14. If I'm doing something right here, which would be b is equal to 11. And then the other smart number to choose would be s equals -2, and then you'd get -a is equal to -6 plus 14. So a would be -8. And so what I can write here is that f at s is equal to -8 over s plus 2 plus 11 over s plus 1. But now, using my table here, notice I've got a number over s plus a here. So I can now use my inverse Laplace transforms, and this would be equal to f at t would be equal to -8 e to the minus 2t plus 11 e to the minus t. And then I want us all to get in the habit of writing, even though it doesn't have it on the table, u at t at the end of this, because this is only correct for t greater than 0. So we've solved the differential equation. So this is the solution to the differential equation. Now, for those of you, again, who've taken differential equations, you could go back and solve it using the techniques you know, and you should wind up with the same answer. Now, as I said, it's not that I'm claiming this is a shorter or quicker method. The whole point is getting used to using Laplace transforms. Oh yeah, getting used to the fact that I'm going to have to do partial fraction expansion again, and then getting back to what the final answer is. Alright, so the next lesson we're going to do another example with this, but we're going to actually just be given what the answer is here. So